staff scientist on the air quality team, where she continues to combine her love of the outdoors with her love of science. And she is someone who helped me and Ava with a project this summer, and I called her on the phone to ask about something. She's like, "Oh, it's super easy. Just switch it in the code like that." And I was like, oh. So I appreciate her math mind and the way she can code. Thanks for speaking today.
Thanks. All right. Oh, I've already changed the slide. Hold on a second. So I'm here to talk to you guys about net radiation, especially the energy balance of the snowpack, and how we can start thinking about how that's going to impact especially wet avalanches, because that was our particular interest. You might remember at a SAW a couple of years ago, we talked about a glide avalanche year we had that was particularly bad. And there was a lot of talk about how those mitigation efforts went out and how it seemed to be at similar elevations, and that got us all thinking about what we should do or how we could maybe better predict this. So I was a senior here, and I worked on a senior project with Ava and also with Max, sitting right here. And we talked about, we got a net radiometer installed at a remote weather station in the, on Tin Can. And we collected that data to analyze and hopefully relate to what we wanted was glide cracks. This is just a rememory slide in case anybody's like, what's a glide crack again? But I'm not going to get into too much detail because I assume most people here know. They're wet events, they're hard to predict, they're hard to trigger, and they're not very well understood. Okay, so we're going to get into the energy budget a little bit. All of the energy on the planet Earth basically comes from the sun, and it comes in as shortwave radiation, which is then either absorbed by the surface or reflected. And it can also be absorbed by the cloud layer or reflected. And then the Earth re-emits that energy as long-wave radiation, which is heat, essentially. So when the Earth re-emits, it can be absorbed, transmitted, or reflected by the clouds or the atmosphere, which then reflects it back down to us, which you might remember hearing about this when we're talking about global warming. This cycle of having more energy getting trapped in the atmosphere and reflected down and then trapped on the Earth and reflected back up is global warming. So we were most interested in the way that this energy budget interacts with snowpack. So we're going to, here's some differential equation, which I have notes on what all these factors are, but there's also the addition version. So we've got the version that is most applicable to the way that most of us are thinking about it, and the calculus. So in the calculus, the L sub I, is we're talking about the latent heat of the fusion of ice, and you're multiplying that by the quantity of the density, freezing and melting rate. So latent heat times the amount that the snow is freezing minus melting. And from that you subtract the integration, so just the sum of the height of the snow over time, the density of the snow at each height by the, C is specific heat capacity of ice, snow temperature across height. So it's okay, you can kind of maybe get a grasp of that, or it's just the short wave in plus the short wave out plus the long wave in plus the long wave out plus the latent heat or the heat of sensible heat exchange, latent heat exchange, and I think P is into the ground. Let me scroll. A precipitation flux, and then the G is the ground flux. So we can measure these first four factors on this energy balance of the snowpack equation with a net radiometer. The short wave that comes in is measured on the top of one of the little arms that you can see on there. The long wave that comes in is on the top of the other little arm. And then the reflected short wave is on the bottom, and the emitted long wave from the ground is on the bottom of the other. So there's four sensors covering four of those factors, and they are the majority of that. So the last four factors on there are much less of the total. Okay, so we wanted to know if we have radiation data, would we be able to model wet slide avalanches on that basis and be able to predict them better? And how does air temperature relate to radiation? And should we be collecting radiation data for avalanche forecasting? Is it useful? Because we've been using air temperature in general to understand how warm it is out there and how much of a wet slide chance we might have. So if we're using air temperature to understand what's going on in the snow, we want to know if that's representative or not. So previous research has been done about radiation and the snowpack and avalanche predictions. So 20 years of data was analyzed, and they didn't find a correlation between avalanche activity and solar radiation. But they only measured shortwave, and most of their slopes were northeast facing. So if the slopes weren't exposed to a lot of shortwave radiation, northeast facing slopes would be mostly influenced by longwave radiation. Then another study in 2013 found that avalanche days had higher incoming radiation than non-avalanche days, so that's a correlation. And they also found that outgoing longwave, which is like heat emitted from the Earth again, is high on avalanche days, which indicates that the snow was warmer. And then longwave was significant on all aspects, but shortwave was only significant on south-facing aspects, which might be why that other study didn't find anything. So just a brief aside to talk about how measurement works, right? There's what's going on in the world. There's like the actual reality of how much energy is in the snow. And then there's us over here trying to figure out how to measure it. So there's no perfect measurement system, and all measurements are subject to being affected by the snow can settle on the top of a sensor and not be able to predict things. So we need to do some data quality analysis or quality assurance to see how good your data is, especially if you only have one sensor in one place, which the first year of the study had. So we looked at albedo as a primary indicator of our quality assurance because that compares two factors that the sensor is collecting. They're looking at the shortwave that comes in and the shortwave that's reflected off the snow. And we know what that should be for snow. It should be near 1. It's a ratio. And snow is very reflective. That's why it looks white to us. So we're like, okay, it should be a pretty high number, but it shouldn't be more than 1 because you can't have more shortwave coming off the snow than is coming in the sky in the first place. So I'm going to show you what it looks like. This is our albedo for the day and the red line, or for the season, and our red line is 1. So we obviously had some instances where the top sensor was blocked because that's the only way to explain that there was measurements above 1. But we can also see that a lot of the time this was in a predictable, an expected range. We also compared with other people who are using the same sensor. There's a team in Juneau who lent us their data, and they also had a bunch of observations above 1. So they're like, okay, this is normal for this type of sensor in this type of situation. So taking all data with a grain of salt always, this is our grain of salt. Moving on. We looked at the relationship between air temperature and long wave as it comes in and comes out. So short wave comes in through the atmosphere and it doesn't, it interacts with moisture at the higher levels of the atmosphere, but it's not directly warming the air above the ground for the most part. It's being transmitted through the air and hitting the earth and warming the earth. The earth then radiates long wave back up into the air, and that's what generally warms the air. You're also going to have long wave being emitted by clouds, which is why a warm, cloudy night as opposed to a cold, clear night. Clouds emit long wave radiation. So that's the long wave in and out, and that's the air temperature. So we have on tin can at the top here, it's a little bit of a busy graph, but you can kind of see that the incoming long wave is jumping all around. That's the green line. It's very reactive and volatile. The outgoing long wave, that's the heat that's being emitted by the ground, is more steady. It's the gold line that's kind of following, and the black line is the air temperature. So you can see just at the very first section on the left, we have a rise initially in outgoing and incoming long wave, and then the air temperature just a little bit over rises as well. And so there's a kind of a following trend all the way through. There's a peak here, further over a peak on air temperature. So it seems to be kind of a delayed reaction, but it's coming through. Down at Mount Roberts, this site at Mount Roberts in Juneau was below tree line. Our site is exposed to much more wind interaction, So that's going to be explaining a lot of the difference between these two sites. You can see that things are tracking a lot more closely at Mount Roberts. The scales are a little off because they experienced different temperatures than we do. So you can see the yellow line that represents 0 is lower on the Mount Roberts scale. So the way these two charts, like the lines stack on top of each other on both of these, is a little different just to line them up. However, you can see the outgoing long wave tracks really closely with the air temperature at Mount Roberts, and the incoming long wave still jumping around but also tracking quite closely. And the incoming and outgoing long wave, or the incoming long wave between these two sites followed each other pretty closely too. I think I didn't include that graph, but it was interesting. So this is taking time out of the equation of the graph you just looked at. So now we're looking at incoming and outgoing long wave graphed directly against air temperature and watts per meter squared. This graph I think is really cool. See if I can, I think this is really fascinating. So up here, this is all of the data that I got from Mount Roberts, and their study went on longer than, or their data set was larger than ours. So there's this wide ribbon of incoming long wave. For any temperature, if you reach in a bag, you could have like a different, it's like 50 watts, 75 watts range for if you reach in at like 0 degrees, it could be anywhere from here to here for the incoming long wave. But the outgoing long wave is a lot closer related to air temperature. As you can see, it's a much tighter group, and there's like these branches going on. And then over here, it just kind of like bubbles off the top. I think that's really cool. But when I restricted their data set to just the same dates as ours, you can see that this is like just one winter, right? You can see it comes up over here. We're looking at incoming again. We've got like a left hand, and then right around 0, it transitions over to most of the trend being on the far side. And the outgoing long wave is like kind of jumbled, and then it all falls into this very tight line. So it goes right at 0 degrees, it takes a left turn and it goes straight up. So the relationship between the amount of energy that is required to change the air temperature changes. This is our site, a tin can, and you can see over here, it's like you can say something about that graph. There's this line where things don't really seem to be on the other side of that line, right? We've got most of our points are over here, but you can't say a lot more about it than that. And at the bottom, you can see I stacked the two on top of each other, just to give it an indication of how far our data ranged on like this graph. So you can see that we had stuff all the way over on the left, farther over than the black got. So it's like we have much lower temperature, or much lower watts for warmer air. And that there's just not as many observations at our site as there is for theirs, where this line is kind of marching up. So this shows us that at two different sites, you can have a very different relationship between air temperature and long wave radiation, which also means that there's going to be a different relationship between air temperature and the snow temperature. So that's a thing to factor in. All right, so we did have some observations of avalanche occurrences. I didn't specify glide avalanche occurrences because it just wasn't enough. There were 25 avalanche days and 65 non-avalanche days in my data set. And this is called a kernel density, or a violin plot, but these are kernel density estimations for each. It's like looking at the top of a histogram, basically. Right here is the mean, then you've got your quartiles, and then you've got your like extent of the data set. So we're saying for avalanche days that there were 25. On average, there was more incoming and outgoing long wave radiation, which is what we expected. On non-avalanche day, or sorry, this is shortwave. So there were typically sunnier and warmer days than non-avalanche days. So that's basically what we expected to find. Not a huge data set, so we can't say anything too strongly about it, but that looks pretty good. Over here we have, for long wave radiation, incoming was lower than outgoing, which is kind of interesting. Not a whole lot lower, but there's some observations were a lot lower. And then outgoing looked about the same on avalanche days and non-avalanche days, which is interesting because the study that we looked at suggested that long wave was more important. That's not exactly what we found, but we're going to collect more data, or there will be more data collected, I should say. So in conclusion, radiometry can provide insights into snowpack energy processes, but we need more data. And there's going to be 2 net radiometers set up for this season, I do believe. And that the main takeaway being that air temperature and snow temperature aren't as closely related as we might assume. So when we're making our forecasts or our estimates about what's going on in the snowpack based on the air temperature, remember what kind of site it is. Is it under the tree line? All right, for acknowledgements, thanks to people who helped me provide with data, thanks to NASA who gave a grant to that project, thanks to Apogee Tech Support who helped me figure out what was going on with the sensor, and a lot of assistance from the staff here at APU when I was working on my project. Here's a slide of citations. Are there any questions? Yeah.
Are there any certain factors you were able to define that correlated with just sort of the spread of data sets from the station here in Turnagain Pass compared to
Juneau?
Mount Roberts?
Well, they have a different type of climate than we do. So that's definitely an influence. They're also below tree line. So it's typically warmer and wetter in Juneau at Mount Roberts than it is in the Kenai Mountains here. And it's also the influence of the trees definitely protects that site from the wind. So the wind exchange is going to have a lot to do with how temperatures are affected. Yeah.
Are actual sensors that you deploy, is that the only way to detect this, or have you looked into doing satellite remote sensing?
So there are remote sensors that detect long wave, and I've seen images of that aggregated over a whole year over the whole planet. I think it would be more difficult to do specific to Alaska. There are ways to estimate the radiation exchange based on cloud cover and the angle of the sun in the sky and some other factors. But it's the best way is definitely to get a sensor. Yes?
So was that trend that changed when the temperature got above 0 with the long wave radiation, was that precedented in some of the other work that studied this?
I hadn't found an indication of that. I think what that was about was that the underlying surface is snow and therefore made up out of water, and it happens right at the freezing temperature of water. So, and I am not a physicist and haven't completely figured out what it is, but I believe it's going to have something to do with latent heat. Yes?
On the big graph where you compared things, did you do any regression analysis on the data set?
I did a little bit. I didn't find it a line that I liked enough to put on there.
Is that because low R-squared values? Or?
I think I'm not well enough versed in the correct way to statistically handle comparing the time series was what I was trying to do first, and I got into a whole trying to tell if one time series predicts another, and I need more of a background and more time to understand it. Yes?
So for your second sensor, is it going to be in a similar location, or how are you going to use it differently or the same as this sensor?
I am not at APU anymore, and this is a senior project that's being continued by other students. From what I understand, do you want to take this one?
Yeah, it's going to be at Seattle Ridge on the existing National Forest station.
So it's going to have telemetry. It's a sunnier site too, so it should be interesting to compare. Yeah.
So I have kind of a question of interest, where you guys are going to take this. I installed two of these down in Juneau, Mike, by the way.
Hey, nice to meet you.
And my whole reason was to try to come up with a way to remotely be able to see when there's near surface basking happening.
Yeah.
So I'm curious if you guys are going to try to tie like thinking about in my daily ops getting rid of sky cover because this is so much better of a tool for me with like even more information on like there's a partly broken whatever. Like
Yeah, get an actual number instead of.
what's going on, looking at these net radiation sensors a lot more than I can't even look it up when I'm sitting like in the sky. So I just thought I'd see if that's
I did.
you guys are thinking about looking at, because I've been trying to come up with ways to see if that's useful for me as well.
I did relate surface horror observations to the radiometry data, and that fit pretty well, just like a 0 to 1 logarithmic sort of regression. And I was definitely interested in going to near surface facets as well, but there weren't quite as many of those observations, and I think maybe they weren't quite as consistent. But yeah, I just used CNFA. I see awesomely provided lots of data, so I've used their observations of surface horror, but I'm sure that it could also work for near surface facets. I didn't get to making that regression, but yes?
Is there any correlation between the ground temperature and the outgoing radiation that you observe?
Yeah, no, I should have mentioned this. Ground, where the surface temperature and emitted radiation is a function, so it's a function of the emissivity of that surface and like one other factor that I can't remember right now, but it is directly correlated. So like the sun emits long wave or short wave radiation based off of a curve that's drawn by its emissivity and temperature. Temperature is the other thing. Yeah, emissivity and temperature.
As a follow-up, is there any indication that long wave radiation can actually soak into the ground through the snow?
Snow is very, very absorbent of long wave radiation, so it doesn't transmit, like even like shortwave goes a little way through the snow and reflects a lot, so it doesn't absorb very much. Like anything that is being radiated is either accepting that, like absorbing it, reflecting it, or transmitting it. So snow with shortwave mostly reflects, absorbs some, and transmits some to like a little layer right below it. With long wave, it's actually almost black, so it absorbs quite a bit of the long wave radiation, and it doesn't penetrate very far at all, like less than shortwave does. Yeah?
Just a question for clarification. When you showed the plot of the avalanche occurrences,
Yeah.
were those all naturals, and what kind of avalanches?
Those were all of the avalanches that were observed by the Chugach National Forest Avalanche Information Center. So that would be, like I assume, skier triggered as well as natural occurrences. I don't believe any of them were intentionally triggered, but they might have been like ski cuts.
So maybe we can see some relationship with incoming radiation the day being out.
Yeah, that might be a driving factor in that, definitely. Considering how small that data set was, I didn't break it into more subtypes of avalanches because that just wouldn't have been a meaningful plot. It would have been like, yeah, there were 3 ski cuts and they happened on sunny days. Like, that doesn't mean much, but yeah. It'd be interesting with larger data set to break it out. All right. I think that means it's lunch, right? No.